Hey guys, so in part one of my videos about invertible matrices, I had just started to explain that these elementary matrices, if we go back to the previous video, the elementary matrices that I described over here, which are obtained by doing one ERO to the identity matrix, they essentially act like EROs when you multiply them onto another matrix. So here was an example that I showed in the last video. The elementary matrix here, the first one, is obtained by permuting the first two rows, and when you multiply it onto a random 3 by 3 matrix, what happens when you do the usual dot product multiplication to find the product here, you essentially find that the first two rows of the matrix A got permuted. Now let me just show you one more example. We did this elementary matrix over here, 1, 7, 0, 1, which was obtained by doing A21 of 7. Well, let's see what happens if I take that elementary matrix, I'll call it E again, and let's say I multiply it by a random 2 by 2 matrix A. Okay? And imagine we do this multiplication. So we just do the calculation, we're going to get A plus 7C, B plus 7D on the top row, and the bottom row is just C and D. So E times A, when I do that multiplication, what have we got? Basically, we took this ERO. We did A21 of 7 to the matrix A. Right? We took 7 times the second row and added it to the first row. That's what we got up here in the first row. Okay? So the EROs really can be encoded by these elementary matrices. Every elementary matrix is like doing an ERO. Okay, we're going to use this concept, the elementary matrices, to explain how to find inverses for matrices that are 3 by 3, 4 by 4, 5 by 5, and so on. Remember that the 2 by 2 matrices, we have a nice criterion, and we have a simple formula for the inverse of a 2 by 2. So none of what I'm talking about here is really needed for a 2 by 2 matrix. But for matrices that are larger, we're going to use these elementary matrices. So here's a definition now, and then we're going to go right into the procedure. We say that A is row equivalent to B. So we have two matrices, A and B. They are row equivalent, and sometimes I like to write this. How do I write it? Just write A with like a squiggly arrow with the word row above it. So we write that as A, row arrows to B. So row equivalent if there exist, if we can find, in other words, elementary matrices. So if there are some elementary matrices, let's say they are E1, E2, dot, 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 up to EK. So there's maybe K of them. So we have some list of elementary matrices here with the property that if you take EK times E sub K minus 1 times dot, dot, dot times E1 times A, you get B. A is row equivalent to B. It's actually a very simple definition. We don't really need to think too hard about it. All it's saying is that if you start with the matrix A and you do some EROs to it, remember these elementary matrices are just like doing EROs. So we have several EROs here possibly, but we just take A, we do those EROs, and we end up with B, then A is row equivalent to B. It just means you can get from one matrix A to B through a sequence of EROs. That's really all it means. Okay? So now here's an interesting note, if that makes sense to you guys. Hopefully that makes sense. Okay? It's simpler than the definition reads. It just says start with a matrix, do some EROs to it, and you end up with another matrix that is row equivalent to whatever you started with. Okay? So now here's a note. If A happens to be row equivalent to the identity matrix, so in other words, if you can start with A and do some EROs to it such that it becomes the identity matrix, that's the matrix with the 1s down the main diagonal and 0s everywhere else, if we can do that, then what does that mean? That just means that you start with A, you multiply by these elementary matrices all the way from E1, E2 up to EK, you get the identity matrix, right? If that's the case, then look what we have here. We have the matrix A multiplied by something giving us the identity matrix. I hope that looks kind of familiar from the first video, as something we talked about in the first video. If we have two matrices, when we multiply them together that give us the identity matrix, then those two matrices are inverses of each other. So this equation right here is really saying that this product of elementary matrices, right, EK times EK minus 1, dot, 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 all the way down to E1, this product is an inverse for A, right? In other words, A is invertible, and its inverse is just this product of matrices right here. The inverse of A is just the product of those elementary matrices. Remember, our goal is to figure out how to find A inverse when it exists. And now we have an idea how to do it. If we can take A and row reduce it to the identity by using some EROs, then those EROs multiplied together give us A inverse. Okay, so that gives us a procedure. Maybe I'll start over up here again. That gives us a nice procedure for finding the inverse of a matrix. I'm going to write down the procedure, and then I'm going to show you an example, and that'll pretty much take care of it in terms of the mechanics of finding the inverse of a matrix. Okay? So here is the procedure. I'm going to leave that note up there on the right side. Okay, so here is the procedure. This is important, guys. Procedure for A inverse. And this is often called the Gauss-jordan method. So the Gauss-jordan procedure for finding A inverse. All right, let me write it down for you. It's actually only 2 steps. Okay, the first step is you are going to form the n by 2n matrix. So you're going to form a matrix that's got twice as many columns as rows. Basically, here's what you're going to do. You're going to put the matrix A on the left side and the identity matrix on the right side. Okay, so this is how you're going to do it. So for example, if A is a 3 by 3 matrix, then you're going to put that here, and then a 3 by 3 identity matrix over here. So it's the size of the identity matrix matches the size of the matrix A here, which is n by n. Okay? And now the second step is just to simply apply EROs, those elementary row operations. So how's that going to look? Well, we're going to start with what I just formed in step 1. I'm going to do an ERO to both sides. Okay, well, I'm going to call that ERO the elementary matrix E1. Of course, when I apply E1 times the identity, I'm just going to get E1 itself. Okay? And then I apply another elementary matrix, which just means I do another ERO to the whole thing. So I'm just doing EROs. Same thing we did in the previous sections. So you just keep doing this, but if at some moment here, let's say we've done a few EROs, and let's say that what we end up with looks like this. We've applied these EROs throughout the entire expression here. If on this side we are able to get to the identity matrix, okay, that's what this definition here says. A is row equivalent to the identity. If A is row equivalent to the identity, then we can make this become the identity matrix. At the very moment when the left side becomes the identity matrix, look what happens on the right side. We get this product right here, which we just explained is A inverse. Isn't that amazing? So you start with A and the identity matrix on the block here first. So A on the left side, identity matrix on the right side. If you can make the left side turn into the identity matrix, at that very moment, A inverse is going to show up on the other side. So let me show you with an example. That's all of the theory of it. Now we just need to practice it on an example. Okay? So here's a quick example of how to do this process. So I'm going to let A be the I'm just going to use a 3 by 3 matrix. I don't want to make it too terribly complicated. So 1, 0, 1, 0, 1, 1, and 2, 3, 6. And what we want to do here is find the inverse, assuming it exists. Okay? So let's go through the Gauss-jordan method that I just described, these two steps. Okay? So the first thing we're going to do is we're going to form the matrix where we put A on the left side. So here's my matrix A. I put a bar in the middle, and then on the right side I'm going to just put the 3 by 3 identity matrix. Okay? Now I just have to do EROs, and my goal in doing these EROs is to try to make the left side become the identity matrix. So let's see what I would want to do. I've got a pivot right here, which is in pretty good shape. I'm going to make this 2 into a 0. So I'm going to use A1, 2 of negative 2. So I'm going to leave the first row alone. I'm going to leave the second row alone. But on the third row, I'm going to take the first row times negative 2 and add it to the third row. So it's going to give me 0, 3, 4, negative 2, 0, 1. Okay? Okay, so the first column is looking pretty good. The second column isn't bad, but I need to get rid of this 3. Okay, so what I'm going to do for that now in my next step is I'm going to do A2, 3 of negative 3. That is, I'm going to take the second row times negative 3 and add it to the third row. So that does not change the first row, and it also does not change the second row. The third row then is going to become 0, 0, and 1. And then what are we going to have here? Negative 2, negative 3, and 1. I'm doing these kind of quickly. You guys can obviously go back and check that I'm doing my EROs properly over here. This is what I'm getting. Okay, so I actually have it in row echelon form now. The bad part about this Gauss-jordan method is that's not good enough. Okay, we actually have to get the left side even better than just row echelon form. We need to actually make it into the identity matrix. So the way you carry on, once you have row echelon form and you're trying to make it into the identity matrix, is you just keep going in the hopes of, in this case, what I'm going to do is I'm going to take the third row and add multiples of it back to the first 2 rows in order to get these 2 1s to become zeros. So in particular, I'm going to do A3, 2 of negative 1, and I'm also going to do A3, 1 of negative 1. So I'm going to take the negative of the bottom row and I'm going to add it to the first row. So the bottom row is not going to change. Okay. But I'm taking the negative of the bottom row and adding it to the second row. So that's going to give me 2, 4, and negative 1 like that. And I'm also taking the negative of the bottom row and adding it to the first row. So that's going to give me 3, 3, and negative 1. I think I got that right. Yeah, that looks good. Okay, I hope that makes sense. The idea is I got my 3 by 3 identity matrix here on the left side, which means the inverse of A is right here. The inverse of the matrix is just, that's what this procedure says, is that if I set up my block matrix here and do EROs, and I get the identity on the left side, then the inverse of my matrix is going to be on the right side. Okay? It may seem like a lot of work to go through that process, but let me show you, once you have the inverse of a matrix, you can solve some problems pretty quickly. Okay, so here would be an example of something you could now solve very quickly by using the inverse of A. So suppose I gave you this system of equations and I said, let's solve x plus z equals 7 and y plus z is equal to negative 1 and 2x plus 3y plus 6z is equal to 2. Okay? That's just a linear system of equations. Of course, we could solve that just by doing the Gaussian elimination from the previous section. Okay, but let's try and solve it a different way. What I want to do is I want to view this as a matrix here. So I'm going to set up my unknowns x, y, z into a column here. I'm going to put 7, -1, 2 here. So my coefficients on x and z are both equal to 1 on the first row. And on the second row, the coefficients of y and z. And on the third row, x, y, and z have coefficients of 2, 3, and 6. See, this is just your matrix A, right? And you're trying to solve for the unknown vector, which I'll call x. And then the right-hand side vector, we used to call that b, right? So this is just ax equals b. That's the way you can translate this linear system. Instead of putting it into an augmented matrix, what I'm doing here is I'm writing it as a times x equals b. And my unknown x is what I would like to solve for. Well, the thing is, since this matrix A is the same one that we were looking at over here, right? So I can find x, remember? X is just going to be A inverse times B. In other words, I want to move the A to the other side of the equation to get x by itself. If A is invertible, I can do that. I just take A inverse on the left side, and of course I calculated it over there, 3, 3, -1, and 2, 4, -1, and -2, -3, 1, times b, and b was 7, -1, 2. Okay, and then we just multiply this out. So 21 minus 3 minus 2, that would be 16. And then 14 minus 4 minus 2 would be 8. And -14 plus 3 plus 2 would be -9, I believe. Yeah, okay. That looks good. One of the nice things about this solution is that if I decided I wanted to change these numbers in the vector b, I wouldn't have to do a lot more work because I already have A inverse. I would just have to change the 3 numbers that are in the vector b here and then just do this calculation. On the other hand, if I had solved this problem by doing the method from the last chapter where you find the A sharp, then the minute I change the numbers that are on the right-hand side, I have like a whole new problem, and I have to like start from the beginning again. So it would be a tedious thing to do. Every time you change the values on the right-hand side, you'd have to solve a whole other Gaussian elimination problem. But here, we only have to find the inverse of this matrix A one time. That's what we did right over here. It was a little bit of work, but we only have to do it once, and now we have it, forevermore. We can use A inverse and multiply it by any right-hand side vector B that we would like. Okay? So that is an example of finding A inverse, and then how you can use it to solve a problem, which I think is really, really cool. Okay. I'm going to write down one last thing. This last part is completely theoretical. It's actually from section 2.8 in the book. There's no homework on this, but I want you to be thinking about conceptually what it means for a matrix to be invertible. So I just want to present something here called, and this will be very quick, the invertible matrix theorem. Okay, the invertible matrix theorem. So here's what we're going to do. We're going to take a matrix A, which is an n by n matrix. It may or may not be invertible. Just any square matrix A. So A is any square matrix. Then the following are equivalent. Okay? The following are equivalent. What does that mean? The following are equivalent means I'm about to make a list. I'm going to list a bunch of things here. And the things in that list will either be all true about the matrix A, or they will be all false about the matrix A. For any given matrix, right? They're either going to be altogether true at the same time, or they're going to be altogether false. They are mathematically, logically equivalent, if I can use that way of saying it. Okay? So let me make this little list for you. So the first thing in the list is just A is invertible. Okay? Okay, so that means that everything that comes below it in this list will be true for an invertible matrix and will be not true for a matrix that is not invertible. Okay? So let's see what some of these statements are. Okay, well here's one. The equation AX equals B. So we were just talking about that in this example here. For an invertible matrix, the equation AX equals B has a unique solution. It has a unique solution, and of course that unique solution is just simply A inverse times B. So I'm not saying anything that I didn't already say before, right? If A is an invertible matrix, then we can solve uniquely for X. There's only one solution to a system where the coefficient matrix is invertible. Okay, and the solution is just A inverse times B. Okay, so there's one point. The next one is basically just a special case of the previous one. Sometimes we like to look at the equation which just says AX equals 0. So specifically the right-hand side, all the constants are 0. Well, that has a unique solution. That has a unique solution which is simply X equals the 0 vector, right? The 0 vector is just being the column of zeros. So in other words, if I changed all of these numbers to zeros, right, then you can see what would happen down here. These would all be zeros, and if I do that matrix multiplication, I find that X has to be 0. Okay, so it's kind of just a simple special case of part B. So for an invertible matrix, only the 0 solution will satisfy this equation. And if A is not invertible, then there will be non-trivial solutions to that equation. Okay, just a couple more quick things. The next one is the rank of the matrix. Let's think about what do you think the rank would be. Well, if you row reduce this matrix A, remember that if it's invertible, of course this is how I'm going to say this in a second, you can reduce it to the identity matrix. Remember that the rank of a matrix is just the number of pivots in the row echelon form of A. Well, the identity matrix would be a row echelon form for A, right? Because you've done EROs to A, and you've come up with that. Well, there's n pivots there. Okay? So an invertible matrix has full rank. The rank is n. There is a pivot in every single column. You know, so if you were looking at the pivots, of course, they would just go right down the diagonal. Every single column would be filled. And in fact, one row echelon form would just be the identity matrix. Okay, that kind of makes sense. So a couple more quick points. The next one just says A can be expressed using elementary matrices. So you can just start applying elementary matrices, multiplying them together, and you eventually will get what capital A is. I won't dwell on that particular item because we're not going to need it very much. And then the last one is just, yeah, that A is row equivalent to the identity matrix. Okay, that was where we started on the theoretical stuff at the beginning of this second video on invertible matrices. I said if A is row equivalent to the identity, then we can show that A is invertible, right? And we go through that Gauss-jordan method. So, all right, so that is basically the invertible matrix theorem for now. I'm going to have a lot more things to add to this list in the invertible matrix theorem later in the semester, but I at least have this for starters. So basically, what should we have gotten out of these videos? We need to know how to find the inverse of a square matrix if it exists. For a 2 by 2 matrix, it's really simple. There's a formula for it that you can just memorize. But for larger matrices, we have to carry out the Gauss-jordan method, which was up here on this side a little bit ago. Okay, just means we're going to do EROs, basically, is what it consists of. So you need to know how to carry out that process. And then I hope you have a sense of why invertible matrices are important. This example here is a great illustration of that. Because if A is an invertible matrix, I can solve linear systems by using the inverse of A. Okay? Guys, please let me know if you have any questions about anything with these two videos that I made, since I wasn't able to be in class to go over it directly with you. I am hoping that you will have watched this by the time we have class again so that we can kind of move forward. But I definitely will take questions. If you have any issues at all about invertible matrices, please don't hesitate to ask. I'm definitely here to help, okay? Thanks for watching. I appreciate your time, and I'll see you guys soon. Thanks.